Okay, let's get started. Synchronous versus asynchronous. Synchronous programming is very straightforward. You execute one line of code and the next gets started when the current line ends. And it's basically the most of the Python applications that you'll come across, and you won't need the asynchronous application for every Python application that you develop. And asynchronous, on the other hand, it allows you to run your long-running, especially input-output operations in the background, and gives the control back to your main thread to execute the very next line of the code. So here's a very trivial example of different models of how concurrency and different models work in Python. Sequentially, we just discussed how synchronous works. You have one actor performing the act in the morning, like cooking the breakfast and coffee, one after another. And then you have concurrent process where you try to boil the water while you're letting the omelette cook. And in parallel process, which is a luxury, you have more than one actor to perform your job parallelly. And we'll be taking a look at the examples, how Python, a small code that I'm using, how it performs when we are using the multitasking versus the multiprocessing in a bit. So meanwhile, we'll take a look at multitasking. And there are two types of multitasking, preemptive and cooperative. I'm sure you must have learned in your college if you did computer science. Preemptive is more where you let the OS control the context switching between the threads. And basically multi-threading is a preemptive multitasking. Cooperative is more where you have the control, where you want the where you want your application to break and let the main thread take control of the next line of the code. Async is cooperative. So why there are so many ways, and why I'm here to talk about the async IO. Multi-threading, there are some cons or limitations. They are not cons or limitations, but what I felt while I was trying to convert my application in Workday to async, I came to know that multi-threading, as we discussed, has no control over the context switching. And I'll show you the example in a bit. And there's also a room for race condition. How the memory management in the C Python works is it's not thread safe. That means if you have multi-threading running, and there's a chance that there's more than one thread trying to change the state of a variable, that could lead to your application in an unexpected state that you wouldn't want. And the next thing is a very complex or very infamous global interpreter lock, which prevents your Python process to run only one instruction set at a time. So it doesn't matter how many, like 10 CPUs in your machine are, you'll only have one thread running at a time. On the other side, async IO exploits GIL, and that's how it achieves the concurrency. We'll see how it does that. So deep down, when you are doing an input-output operation through threading or any synchronous application, what happens is a lock, a GIL is acquired to run those instruction set. And GIL, what it does, it handovers the job to the low-level system calls to take care of the input-output operations concurrently. And in a multi-threading environment, if you have one thread just waiting for the input-output to complete, all other threads are just waiting. So what does async IO do, and is GIL ever released? It does when the IO task is being performed, the GIL lock is released, and as I said, the low-level system calls take care of the operation, and the lock is acquired when the data is received in a form of Python object. And here comes the async IO with the components like coroutines, futures, task, and event loops that we'll take a look in a bit. Takes advantage, they acquire the lock and give access to the main thread to be able to run the next available coroutine or the next available line of code. Take a look at an example. I just ran it outside. I was not able to connect to Wi-Fi, but we have two examples, the async example and the multiprocessing example. What they're doing is they're fetching, they're going and doing the get operation on two websites 80 times each. And with the multiprocessing example, you can see it finished, even though it is utilizing 4 processors. It took 2.65 seconds, and it can vary depending upon how loaded your machine is. And on the other side, don't worry about the source code. I'm not going to explain it right now. Don't have enough time. 30 minutes only. Just an example. I have those examples. I can provide you the slides in the end. I'm also available here throughout the day if you want to have a chat or take a look at the code. So yeah, the async code doing the same job in 1.07 seconds while utilizing only one thread, keep in mind. And on the other hand, the multiprocessing library is taking 2.65 seconds. It is the fastest I could find because I closed all other my Google Chrome and other applications. Basics of async I/O, the coroutines, event loops, and the task. We'll take a look at them one by one. Coroutine is your normal Python function. It only has the power. Well, the power is it can pause the execution. That's it. And there are 2 keywords being used to do that, to achieve that. That is async and await. Event loop is nothing but a queue where your coroutines are placed in order, and event loop does in an iterative way go through each coroutine, and if there is any input-output operation performed by any coroutine, then what it does, it lets the input-output operation go into the background, and then the event loop, working with the task and futures we'll discuss, gives the control to the next coroutine, and that's how the asynchronization happens. A simple example, this is not how async program will look like, it's just a pseudo example. You have a method which is doing some CPU bound task and then input output and again then CPU, and then you launch three instances of that task. You put them into the event loop, and you can see in the timeline, the task 1 starts running the CPU bound operation while the other 2 are waiting. And when the task 1 goes and starts running the I/O task, the task 2 comes in and starts running the CPU bound operation. And that's how it's saving the time and not letting the other two coroutines wait, and utilizing the time. And that's how the concurrency is achieved in the async I/O application. So far we figured this, what is synchronous, what is concurrency. We know how GIL is being exploited, and we know the coroutine and event loop. We'll start looking again. It's a duplicate. Don't worry about it. Just to bring again the keywords async and await, and we'll see the examples now. So async. Async, when you put in front of def, your function is converted into a coroutine. That's the only job, simple and straightforward. And the next step, highlight you see here is the event loop being created. When you use async io.run, you create a fresh new event loop, and then you're passing your coroutine in it. And the job of the event loop is to manage the life cycle of the coroutines and clean up after it's done, and also it acts as an entry point into your async application. Now we introduce await. Await has the power to pause and wait for your coroutine. It does not enable you, it does help you in concurrency, but it's not just the await and async will let your program convert into an asynchronous program, but await does let your coroutines pause. Here you will see 2 coroutines here. The second one, the top one, the add one is just doing the CPU bound operation. It's not doing any IO. The first coroutine here, the hello world, we are imitating an IO operation by using the async IO sleep. Async IO sleep is different from time.sleep. Time.sleep will pause your main Python process, but async IO pauses your coroutine in which it is mentioned. So the line number 7 will pause the hello world. Now we have the entry point event loop here, async IO run, and we are passing the main method into it. And what it happens within the main, if you have multiple coroutines awaited, then all those coroutines will go as a queue inside the event loop. And when you run this code, when it reaches line number 11, it pauses and waits for hello world to complete. When it reaches 12, it pauses and waits for the add one to return. Now this is not asynchronous, this is pretty much synchronous. It's pausing, nothing is running around the same time. And we do have a coroutine add wait here. Yeah, it doesn't. So now we introduce the task. Task is very nice concept. I'm still reading about it. Implements the futures. Now, what is future? Future is a Python object which does not have any value when it is started. It's a future because when a value is assigned to a future, it resolves. It's the future. When the value is assigned in the future, it resolves. So what happens when you when tasks are implementing the futures, you put your coroutines into the task here. Here in the line number 13, what we are doing is, it's the same code from last slide. We are putting the coroutines inside the task, and then then everything happens implicitly. You don't have to do anything else other than just create the task. And here on the right side, on the timeline, you'll see how the concurrency is achieved after you create the task. So when you run this program, the main method is called, and it goes, then it pauses as soon as the await message, the coroutine is awaited, the line number 15 is executed. So the main goes into the pause, and then it runs the hello world, which we awaited here. And when the program, the runtime environment is running the hello world, it encounters the line number 9, where we are replicating an IO job, which is taking 10 seconds. That's a long time of wait. And since it's a task, it's a coroutine within a task, it automatically gives back the control to the event loop, and event loop then goes on to the next coroutine available, which is the add +1, and it starts running at the same time. So I'll quickly show an example here. So my coroutine with task and my coroutine without task. So without task, only one coroutine is called. Can you see? Only one coroutine is called, and we are waiting for 10 seconds. Let the input-output operation finish, and then you can see after 10 seconds our second coroutine is called. And now with the you can see both coroutines are called instantly. We are not waiting for the input-output or sleep, async IO sleep to finish. And that's actually the asynchronous programming, how you do it with the simplest program available. Canceling the task, so oftentimes you would have an input-output operation that would run longer than you desire. It happens very often actually. And you would want to have a timeout setup that you don't want to waste your resources. And for that, we use the await for, which is inbuilt in Python async IO. And sorry, I forgot to mention I'm using Python 3.10. And there's been some changes in Python 3.11, and it has become very easy. You don't have to make it more complex. Things are very much self-explanatory. We'll see them. And so, for example, you create the task, you do the same job, you create the task, you put the coroutine, and then you pass the task into the wait for function, and you pass how many seconds you want to wait for. And when the time exceeds the timeout, it fails. It doesn't fail. The control is given back to the next coroutine available, and a message is logged that task didn't complete and the exception encountered. And then we have shielding. So there are some cases where you wouldn't want the coroutine to cancel even if the IO operation is taking long. You just want to know in the logs You just want to be monitoring that things are taking long, and for that we use async IO shield. So wrapper inside a wrapper inside a wrapper. You see coroutine passed in a create task, creating a task, then passing it to the shield. Shield is passed to wait for. Again, this is a bit complex, but things are getting better in new versions. So here we see when the timeout, when the operation exceeds the timeout we define, it doesn't break. We can await again the coroutine to let the IO operation run. So it's a duplicate slide, just showing how things look in 3.11 Python. You just have a context manager where you can use the async IO timeout and just pass your how much time you want to wait for your operation. Things are getting better. And shielding the task again in 3.11, it's very, very simple. You just create the task, pass your coroutine, and await the shield passing the task in it. Now, before you go, if you're interested, go and start looking for what you can convert into asynchronous programs. Keep in mind there are many things that you need to be aware of. If your application is very much CPU bounded, it's mainly performing the CPU bounded operations, you don't necessarily need to do it. It won't make any difference. But if your application is very much input bounded, like mine was, very much depended, the one iteration of checking 53 metrics from Wavefront, Grafana, Salesforce, it was taking about 90 seconds and it got down to 8 seconds. So it helps when you know for what application you'll be using it. And the question I heard the last time, when you're developing an asynchronous application, you don't need to convert all your methods into asynchronization. You can keep a balance. Just focus where you have the IO operation and just focus there to use the asynchronization over there in that module. And there is also a debug feature that you can pass in your event loop, and it will tell you when there is a lot of time being taken and there was no long running operation as such, the IO operation, and you will know that my method, which was just doing the CPU bound operation, was not very helpful using the asynchronization for this. Now, reference materials, I use this book. It's very helpful if you want to get started with asynchronization. The explanation is very simple. I read so many blogs online and none of them were making sense. If you are like me, you want to know how the wheels turn, you want to know the background of it, this is very detailed. Jupyter notebooks and asynchronization. With the IPython 7 plus version, it's great. You have inbuilt integrations with the async IO. And you wouldn't even have to create the event loops. You just create the task, you know now, and just directly you can await your code inside the notebooks. We'll see it in a bit. But that being said, there are some limitations. The work is still very much experimental. There's some good work done by the giants in Python world. They built the Curio library and the Trio. I tried figuring out for some time, but I wasn't getting I wasn't making the sense, and plus my code wasn't that. Since I moved to M1, things are changed. My code doesn't work now. So Jupyter and task, that's how you can get started. So we are looking at a small program. Here you can see, I copied it from Google. We just create a coroutine by adding async keyword, and then we are just awaiting the results of session, which is again a coroutine. So good thing about this library, it is async, compatible. And there's also the request library, which is now async compatible, request-async, which is very new. And there are many libraries which are moving on, and they are bringing the features of the async compatibility with the libraries. And here, coming back to this, what we see here, I'm not creating any task, I'm not creating any event loop. I'm just using this library, which is already pre-configured, have their core routines in the library, the compatibility, and I just await the coroutine, and when I run it, it does the job. Okay, it ran. And if I just go back and pick my code where I ran the coroutine with task, and I just copy paste here, and if I run it on the Jupyter notebook, I see an error because it says can't be called from a running event loop. Implicitly, Jupyter notebook is running an event loop for you, and that's why I said you don't need to create explicitly. You just create the task and you await them. That's it. It's really easy now with the notebook. So when I do this, you can see both the coroutines were called, and that's how the asynchronization, the minimalistic way you can run. So the best part is with the Jupyter notebooks, you don't have to learn many things that are complex to get started quickly. And using the Jupyter notebooks, you can experiment and play around the async IO library. And I think you don't even need to import this one. I just did it.
Hello. Nice talk. I have like two questions. First question is like, do you have any recommendation for figuring out like what type of machine to use for async IO? For example, when you're using a multiprocessing, we normally tend to have a number like, say, if there are 8 cores, you tend to have like a 17 kind of processor so that you get best out of the machine. Do you have any kind of suggestions for like choosing a best machine to get, if you have a machine, how to get best out of it using async IO? That is one. Second is, what are the debugging and the observability tools available while deploying async IO application in production? For example, what if a coroutine is always not performing the work and sleeping? Is there any kind of debugging and monitoring tools available in production to find the performance / like coroutine or all of the problems? Yeah.
So you'll have to repeat the question 1, but I can answer your question 2. At this point of time, you can create, so what I did, I had the shielding and canceling in my code, and I hard-coded the metrics which I was sending back to the wavefront. And that was it. I didn't have to like enable any profiling tool to be able to figure out how much time I'm spending, my coroutine is spending. And yeah, that's pretty much simple, the straightforward task I did with canceling and shielding. Could you repeat your first question? Okay.
Let's say you have a machine. Right now, it is possible to spin up as many number of coroutines as possible if you're running, right? But there will be some kind of a saturation. Let's say you have 100 coroutines is performing X. When you have 10 coroutines is performing best. Right? Do you have any kind of guidance how to figure out what is the right number of coroutines for a given machine?
That's a really good question. I forgot to mention, in Python 3.11, there is a feature called task group, where you have a way to put all your related coroutines in a module in one context manager. And you can make sure that all coroutines are part of a group and they all go in order before the next group begins. So I think that's the way you can group them together and make sure that they're all in different modules, and make sure that they're finishing as a group altogether. Yes.
Thanks for your talk. Sorry. So I have also 2 questions. First is about the adoption of async for a common library. So if you can just go there and use like request, for example, because it also is not fully compatible with async programming. So my first question for you is, how do you see this adoption of async by common libraries that are used abroad? And I can ask the second later if you want, so I don't break our flow.
So yeah, that's a good question. I started looking into async about 2 years back, and the request was still in work in progress. Even as we stand here, the Jupyter notebook is not fully compatible in running your asynchronization code on their website. I hid a site, that's what it is mentioned. But the adaptation is very fast, and even the enhancement in the way the complexity is reduced by Python developers, it's great. It took me some time to bring this concept in my team to be able to like have everyone start looking into this. And around the time that I was starting, I had the same issue. Very few libraries were supporting async. I don't have an answer how, like we as a developer, other than just we start using their libraries and we start using async IO more. I think it will help in the adoption. Even if you go onto the Google, you won't see that many articles. People are talking about asynchronization. The basic they'll cover is talking about parallelism and then throw a big code in front of you, and made no sense. I think it's getting faster. The adoption is getting fast, but how long or how fast we can grow, I don't have no answer, to be honest.
Sorry, it's going to be really quick. So second question is about, for example, if you have a very complex set of requests made to REST API, and somehow you need to limit like the amount of asynchronous processes running at the same time because you have some limitations on the API, for example. So is there any sort of implementation of something like traffic lights that you see as possible so you can kind of control the flow?
So how async IO works is you're still on one thread. You're not on multi-threaded. So you are already limited. You can put as many coroutines in a event loop you want, and they will not pause until the coroutine before the coroutine before is performing an IO operation. So that is a factor which is helping in trying to limit your multiple coroutines running and creating a chaos. So that's an advantage between the threading and multi-threading and the async IO. The slide I was talking about where I was comparing, I didn't list those problems here. You see, there's no issue with the race condition here because it's running only one instruction set. And again, with the global interpreter lock, it's only an advantage to the async IO, not a limiting factor. So put as many coroutines as possible.
Hi, thanks for the talk. Two of the things I wanted to also, and not answer, like I wanted to share my experience on it. So one is the saturation of the machine. So what I found out in my earlier experience, so one of the work in my one of the project I had, so it was calling millions of times to an API. So, but coming to the second question, like if we can limit those API calls. So what we did is we used semaphore to limit certain number of calls at a time so that we don't saturate our machine as well as the IO we are calling into. So that was a good thing I think whoever works on it found. And another thing is, sometimes we use not async IO compatible code, but we have to run it in async IO mode because of other coroutines we wrote. So we mostly for those kind of situations we use run in executor mode so that it kind of behaves like async IO, but not actually running in asynchronous mode. So just wanted to say this.
That is what it was in the example. But yeah, I agree with the first point you mentioned. With async IO, it doesn't limit you to use with multiprocessing or multi-threading. You can still incorporate in async IO with the other models of concurrency.
Could you talk a little bit about debugging? Because it sounds like you've had a lot of experiences, and I'd be curious to know like where you got stuck and how you resolved those debugging and asynchronous.
So what I did, everything in here in the slides is from my experience, and for debugging what I am doing three things that I discussed. Monitoring how long your IO operations take. You can use the shielding, log them, and if you want to put the metrics on any monitoring tool, you can create the metrics and put them on wavefront, let's say. And for debugging, I don't use this debugging method because I know that I'm not going to use async for any of the CPU bound operation. So when I'm talking about the tool that I work on, it's very much IO bound, and every other call, I mean the 90% of the calls are being made are IO based. So I just use the async module against those operations. And in order to monitor, debug for later time, I just use shielding.
Time for one last question. Anyone?
Hello. I have one basic doubt. Like, I'm always confused in these concepts like multi-threading, multiprocessing. So, for example, you talk about multi-threading is of two types, right? CPU bound and IO bound. So, like GIL restricts CPU bound, but GIL doesn't restrict IO bound.
Yes.
So, when you said that async IO exploits GIL to use make coroutines, that part, can you please elaborate again?
So by exploiting, I mean when your global interpreter lock is running the instruction set, and if that is an IO bound operation, the lock is released. I mean the Python, the runtime is not doing anything at that time. All the work is being carried on by the OS level, the way the notifications in the OS work. So OS, suppose you have a server with which you are talking to, you open the sockets between the two, and you let the GIL hand over the IO task to the operating system, to the socket level, and there the operation is happening concurrently. It's not synchronous. And GIL then goes back and releases the lock, and deep down the system calls are managing from which client certain request came in for the IO bound operation, and when the data returns, the OS notification system hand over back the data to the Python runtime, and during this time the global interpreter lock is released, and that's where you bring your async IO task and event loop and futures to take care of. So the async IO uses the futures via task, which is just waiting for that future value to be set when the data has come back from the server. And meanwhile, your event loop is like maintaining the life cycle of all the coroutines. With every iteration, it knows which operation is being held and which coroutine is not working right now, and it just moves the control of the main thread to the next coroutine available.
Thanks, Simar. That's it. Thanks.
You done? Thank you.